Okay, let's go ahead and get started. We have a lot of fun things to do today. We're going to start talking about transverse standing waves, and these are the basis of all stringed instruments, your violin, your guitar, those types of instruments. On Thursday, we'll talk about longitudinal standing waves, primarily sound waves that are in organ pipes and flutes, things like that. And so would someone be willing to get us started with a prayer? Is there a prayer with us? Comments?
Our dear Heavenly Father, we're very grateful to be here at BYU. We love you very much. We're very grateful for thy son, Jesus Christ. Father, we're also very grateful for Professor Francis, and we ask for the blessing of health to be on him and his family, and that he can get over this cold very, very quickly. Father, we also ask for a blessing to be upon us as we're learning physics and learning the material of the other classes that we're in, that we have an added measure of, and gift of the Holy Ghost to be with us. So remember what we're learning that we recall when we take our tests. Father, we love you very much, and we're so grateful to be here at BYU. And we say his name is Christ, amen.
Okay. Before we go to the new topic, let's make sure we understand the old topic. Let's see if this will be well. So talk to your neighbor.
Oh, good. That would find it sound just.
Okay. We're back live. Everyone, take out your clicker. Let's take some attendance.
You look kind of familiar.
Hey.
One of those, please. Last time we were here,
AA. So I took her in Idaho. Yeah, mine was I didn't have
Okay, last call. Get your points. Okay, we're here. So
I just like easier.
I'm sure you noticed that in the back of that chapter, well, there were equations for the Doppler shift, equations that you're not going to use either on the homework or in the exam. What you need to understand is the qualitative details of the Doppler shift. And it's really quite simple. These are the three things you need to remember. If you're going towards the source, the whistle, the siren, whatever the source is, if you're going towards that source or it's going towards you or both, you're going to hear something higher than what that source is making. If it's making a sound at 400 hertz, you're going to hear something higher, maybe 408 hertz, okay? And if you're running away from the source or it's running away from you or both, then you're going to hear something lower than 400 hertz, maybe 390, okay? And here's the thing. That shift, either up or down, that's the Doppler shift, does not depend in any way on proximity, on how close you are to the source. That has nothing to do with it. All it cares about is the relative velocity, okay? If you're going towards the source at 60 miles an hour, it's going to be shifted up from 400 maybe to 410. If you're only going 30 miles an hour, maybe it's only shifted from 400 to 405, okay? The shift gets bigger as the speed gets bigger, but not as you get closer. As you get closer, it just sounds louder. You've known that since the second grade, okay? But that's very different than the frequency. The volume is how hard those wavefronts are pounding on your eardrum, okay? The frequency is how many times they pound on your eardrum each second. See if your neighbor understands the difference.
Maybe a little bit.
But we're gonna do cheaper. Raise my head on like. Yes. Like.
Okay.
Like higher additional frequency. Yes. Yeah.
What we're going to talk about today is a resonance phenomena. And this is also something that you're familiar with. You know, when you're pushing your kid, brother or sister on the swing, you know that there's a frequency at which they want you to push that's going to put more energy into the swing, make them go higher and higher and higher until you get in trouble with your mother, okay? And if you push at any other frequency, you're just going to make them mad, okay? Because sometimes you're pushing in a way to make them go higher, and sometimes you're pushing in a way to slow them down. And so there's a certain frequency at which they want to go back and forth. And if you push at that same frequency, the energy in the system will get larger and larger and larger. Now, the most common example of this that's presented is the Tacoma Narrow Bridge. And this Tacoma Narrow Bridge had a really bad morning where a windstorm, and it wasn't really a terrible windstorm, it was 42 miles an hour, which is, you know, that's nothing for Montana. Anyway, the bridge was built in just such a way that the wind caught the side rails and swung that bridge back and forth at just the right frequency at which it wanted to rattle apart. Now, I don't know if you've ever experienced this rattling apart before, but I used to drive a 1979 Chrysler Cordova. I mean, a land yacht. And that thing, if I was going 55 miles an hour down the freeway from Bozeman to Belgrade, it hit those brakes in the road at just the right frequency that the car wanted to rattle at anyway. And so by the time you got about 2 miles down the road, you were just falling apart. And so you had to go either faster or slower to get a different frequency of those brakes in the road. Now, you see that what happened was the bridge fell apart. It just completely collapsed. And here's what it looked like while it was oscillating back and forth. Okay, now, at some point in your career, your academic career, they're going to show you the movie of this. It's 30 minutes long. I am not going to show you that movie today. I would rather show you Groundhog's Day than that. Okay. So let's talk about standing waves. That was a traveling wave, okay? The energy and the momentum went across the room, hit your eardrums and assaulted your eardrums. And that's what we have been studying. A standing wave is very different. A standing wave is more like elbow, elbow, wrist, wrist, okay? It's just an oscillation, but it happens at certain frequencies that are resonant with a system. And I'm going to demonstrate this with this spring. if I just do this at any random frequency, that spring is going to fight my hand, and it's just going to be pulling and fighting me. But it turns out that I can find certain frequencies at which it doesn't fight my hand. If you look at my hand, it's hardly moving. And you see that what we have is one antinode. In your reading, you know that where it's tied to the podium down there, that's a node. And my hand is pretty much a node. We call it a quasi node. The middle, where it's got the maximum oscillation away from equilibrium, we call an antinode. I call it a football. Does it look like a football? Okay. Now, if I wiggle my hand a little bit faster, it starts fighting me again until I get to a frequency where I get two footballs. And we call that the second harmonic, the second resonance, if you will. There's two footballs. And now if I go a little faster, it starts fighting me again until I, come on, you can do it, Greg, until I get three footballs. Now, I'm not sure if I can get four footballs. That's just not humanly possible, but let's try. Oh, no, that's not a four football. There we go. Okay, we'll just leave that down there. So, I said this was a resonance phenomena. If we think about what's happening there, if I send a pulse down that spring, when it meets that fixed end at the other end where it's tied to the podium, we know that it reflects inverted. It comes back on the bottom. And when it comes back to my hand, if my hand is really acting like a node, like a fixed end, it's going to invert again. And so this is just like pushing your kid, brother, or sister on the swing. Okay. If I wait until that pulse gets all the way down and back before I send another pulse, I'm putting energy into the system. And the amplitude gets bigger and bigger and bigger. And that's what we mean by a resonance, So let's figure out what that frequency would be. So if I figure out how far it has to go, well, if the spring is length L, capital L, it's got to go 2L, down and back, right? Down and back. And so that means the time that it's going to take, the period of that, is going to be 2L divided by the speed of the pulse. Now, I hope that makes sense to you. If you were going on a road trip, say to Montana and back to Bozeman, and it's 400 miles, and you're going to average 50 miles an hour. Well, you just take the 400 miles, you divide by 50 miles an hour, and you get 8 hours. That's what it's going to take to get you there. Okay. And that's what we've got here. We've got the distance 2L divided by the speed at which it's going. And we have a formula for that speed, right? The formula for that speed for a transverse pulse on a spring or a string is the square root of the tension divided by the mass density. Well, the mass density of this spring, the mass per unit length, well, that was decided when it came off the factory conveyor belt. Okay, that's fixed. But the tension I can change by pulling it tighter or loosening it to change the speed. Okay, now L is the spring length, V is the speed of the pulse. What we usually care about is not the period, but the frequency. But if you know one, you know the other. The frequency is just 1 over the period, and so it would be the speed over 2L. Now, this combination of variables is going to show up over and over and over again. So you might as well give it a name. Call it Charlie. Okay, that's one Charlie. One Charlie. Okay. Now, I was only able to go up to the fourth harmonic because I am human. So we're going to try to get rid of the human here. And what I've got is we spared no expense. We went right down to Home Depot and got this Black & Decker jigsaw. But we're going to create a node here. And here it's going to go up and down, but not very far, kind of like my hand was going up and down, but not very far. And so we're going to create a quasi node over here. Can you see that over here? Can you see it over there? Okay, in the back, I don't care. You chose those seats. That's on you. Okay. Okay. So I'm trying to get the first harmonic. Let's go to the second harmonic. Okay, where the amplitude of the footballs gets big. And then if I go a little bit higher frequency, it goes away. Until I get to the third harmonic. And then we can go to the fourth harmonic. That's what Greg was able to do. Then we go to the fifth harmonic. And the sixth harmonic. I can't hold it much longer, Captain. He's breaking apart. Okay. Now, I want to teach you something about the football, but in order to do that, I need to slow down time. And so I'm going to go back to the third harmonic. Okay. And I'm going to put a strobe light on that to slow down time. Now, some studies have shown that a strobe light can trigger a epileptic seizure. So if you know that you are prone to epileptic seizures, you're going to want to close your eyes while we do this part. Okay? Let me. Anyway. So there we go. Okay, now you can see that whenever this football is going down, its neighbor is going up and vice versa. And that's going to always be the case. They're always going a different direction from their neighbor. Okay. So they ask you, can your professor stop time? What's the answer? Yes. He's amazing. Oh, that's not what I wanted to do. Let me get this out of the way. Give us a little bit more light here. Okay, now the question becomes, if these waves are standing, not going anywhere, why do they obey the wave equation? I mean, you remember the wave equation. We've been using it over and over again. It tells us that the speed of the wave is equal to the frequency of the wave times the wavelength. If this isn't going anywhere, how can I talk about a speed? And to answer that, I'm going to do a little demo with this wave machine. And I've clamped down this last bar here. And I'm going to send a wave, a traveling wave, to your right. And you're going to see it move to your right down to the end. And then it's going to bounce and come back. And once it comes back, you're going to have two traveling waves, one going to your right and one going to your left, that interact with each other through superposition. And when that happens, what you're going to see is a standing wave. Okay, let's make that happen. There's the traveling wave, then it bounces. There's the standing wave. Okay. So a standing wave is really two traveling waves that are identical to each other, traveling in opposite directions with the same frequency, same wavelength, same amplitude. Now, in 1992, I asked my grad student to make a video for me of these standing waves. And Bill McHarg, he dropped out of school, okay? I got to tell you, it just dropped out. And the reason he dropped out is because he got caught up in this new fad, this new thing that was going around back then, computers. I told him that's never going to catch on. But he left the university and went to Silicon Valley. And now he's so rich he could buy 11 countries if he wanted to. But this video that he made for me is very primitive because back then there weren't programs that would make videos for you. He had to do this pixel at a time. And so please be patient with it.
Here we show the superposition of two oppositely propagating but otherwise identical sine waves. The blue wave propagates left to right, whereas the green wave right to left. The bottom trace shows their sum. The addition of these two waves result in a wave that oscillates but stands still, hence the name standing wave. The dashed lines are positioned at nodes of the standing wave, points that do not oscillate. These represent, in the case of, say, an acoustic cavity, rigid walls, or in the case of an optical cavity, reflecting mirrors.
So that's why we can use the V in the wave equation. Now, in summary, standing waves arise from superposition of identical waves traveling in opposite directions. It only happens at certain frequencies. It's a resonance phenomena, like pushing your kid brother or sister. And the nodes we call the places where there's zero vibration. The antinodes are where we have maximum vibration. Okay, the footballs, if you will. Now, let's look at the different the different, I'm losing my words, resonances. Okay, so this first one, we sometimes call the fundamental. It's also the first harmonic, And you see, we've just labeled different times. At time one, maybe noon, the spring looks like that, then it looks like that, and then at 6, it looks like that, and then it goes back up to 1. Okay? Now, the name of the game is, what are the resonance frequencies? What frequencies will this spring resonate at? And the thing is, I can't draw a frequency. I can hear one, but I can't draw one. So instead, I draw wavelengths, and then I use the wave equation to find the frequency. Let me show you. I've got to have a node here and a node where it's tied down there and an antinode in between. And so I've got one football. Now, this is something that you can take to the bank. You can put in your toolbox. It'll always be true. It takes 2 footballs to make a wavelength. Tell your neighbor how many footballs it takes to make a wavelength. Does it always take 2? Yes, it always takes 2. Always takes 2. Okay, so how many wavelengths do I have there? I got a half wavelength, okay? That's only half a wavelength. And if I let L, capital L, be the length of the spring, that means my capital L is just half a wavelength. If I solve that for the wavelength's going to be twice the length of that spring. And if I put that into my wave equation, I can find the frequency at which I would have to wiggle my hand to make that happen. Now, the second harmonic has 2 footballs. And you see, this is what we saw with the strobe light. When this was in 1, when this is in position 1 up, this one's in position 1 down. And when this is in position 6 down, this is in position 6 up. They just go opposite each other, okay? Now, it takes 2 footballs to make a wavelength. So what I've got is, I got 1 wavelength there, okay? If that's half a wavelength, then there's the other half of the wavelength. And so my length of my spring is going to be 2 times lambda over 2, or just lambda 2. And I've got this 2 here to tell me that's the wavelength of the second harmonic, the second resonant frequency. And we notice that that's half as big as the original wavelength. And that should just make sense. That should speak to your soul. I'm fitting twice as many footballs in the same length. Those footballs have to be half as big if I'm going to fit twice as many in there, okay? Now, if I go to the third harmonic, I've got 3 footballs. I have now crammed 3 times the number of footballs into the same length spring that I originally had 1 football. So what do you think the wavelength's going to be now relative to L? Yeah, let's do it. Okay, so that's going to be lambda over 2, or half a wavelength. I've got 3 of those in a length L, and that's going to give me 2L over 3, where 2L is just the wavelength of the first harmonic, the fundamental resonance. Check on your neighbor. Do a buddy check. Check that your neighbor is with us.
Like I'm surfing on like I said,
Usually it's a lot of so that is because
Okay,
like describing the way
so here's the summary. The fundamental wavelength is the longest wavelength that will fit in the system. In this particular system, it was going from a node to a node. It only had 1 football in between. And so the first harmonic had 1 football, and that means the wavelength was twice the length of the spring. Now, As I go to higher harmonics, the second harmonic has half the wavelength. The third harmonic has a third the wavelength. The fourth harmonic has 1/4 the wavelength. The fifth harmonic would have 1/5 the wavelength. And that shouldn't be something you remember. The fifth harmonic has 5 footballs. If I've got 5 times the number of footballs squeezed into the same space, they got to be 1/5 as big, right? Now, if I use the wave equation, the speed of the waves on that spring, that only depends on the tension and the mass density. That's not going to change. That's not going to change. And so that means if this wavelength gets smaller by half, by a third, by a fourth, the frequency has to get bigger by 2, by 3, by 4, by 5. So that means if my fundamental frequency, if my F1 is 12 hertz, my second resonant frequency, my second harmonic would be 24 hertz. My third would be 36. My fourth would be 48. You see the pattern? Okay. Again, check with your neighbor.
Stretches.
Okay.
I was.
I need to talk about a wrinkle. In the physics department, we talk about standing waves. And in the music department, they talk about standing waves. But we don't use the same language. We would call this the first harmonic, and the music department would call that the fundamental frequency. Now, in the physics department, we often adopt that language and call that the fundamental. We go back and forth. Fundamental, first harmonic, they're the same to us, okay? But the second harmonic for us has 2 footballs, and the music department would call that the first overtone, okay? And I'm not saying that they're wrong. I'm just saying that we're right, okay? That's what I'm saying. Now, this one we would call the third harmonic, and they would call it the second overtone. And that's because we want to use this formula here where the third harmonic is just 3 times the fundamental, 3 times the first harmonic. If I said that the fundamental frequency was 10 hertz, and I asked you what's the 23rd harmonic, you could just say, oh, well, it's 23 times 10, 230. You could use that simple equation, okay? Now, how many of you went to Germany on your mission? Raise your hand. Okay, there's someone brave. And I know some of you have gone to Germany and you're just too shy to raise your hand. So if you're teaching someone on the erste Geschock, the first floor, do you need to go upstairs in Germany? Yeah, okay. Because the first floor is up 1 flight of stairs. The ground floor, the Erdgeschock, they call the ground floor. And so it's ground floor, first floor, second floor, third floor, like that. Again, Germans aren't wrong. They're just different. Okay. Freilich. Questions on that? We're going to go with first harmonic, second harmonic, third harmonic. So let's look at a sample problem, a pretty easy one. A string is stretched between 2 fixed supports, and we set up a standing wave with 2 nodes between the ends when we drive it at 240 hertz. Let's draw a picture of the standing wave pattern. What's the fundamental frequency? At what frequency will the standing wave have 3 nodes between the ends? So let's give ourselves some room. Okay. So I'm told that the endpoints are nodes. They're tied down. And that I have two more nodes in between, and they have to be evenly spaced. Okay. And between any two nodes, oh. Okay, don't touch that. Between any two nodes, I have to have an antinode, a football. And so this is going to look like this at noon. And then 1/2 period later, it will look like this. Oops. Well, you know I can't draw, right? Okay. So clearly what we have here is the third harmonic. There's 3 footballs there. And we know that that's 3 times the first harmonic. We also know that it's 240 hertz, because that's what we were driving it at when we got this. That's what the jigsaw was doing, 240 up and downs per second when we got this pattern. Okay. So what number times 3 gives you 240? That tells me that F1 is going to be 80 hertz. Now, if we want 3 nodes in between the endpoints, let's put the endpoints in there again. Now it's going to look like that at noon, and a 1/2 period later, it looks like that. And that's going to be F4, which is 4 times F1, or 4 times 80 hertz per second. That's 320 hertz. See if your neighbor found that trivial and would love to see that problem on the next exam. Yeah. Talk to your neighbor.
Like that. Like,
Are there questions?
I get it.
Okay. You know, in this class, that just as soon as I get you feeling really, really comfortable with something, I pull the rug out from under you. Okay, and that's what we're gonna do right now. Let's look at this problem here. In some places in the country, you can actually make music with a hacksaw blade by clamping it to a post and twanging it. And, you know, if you've got the right boots, it works just fine. So we've got a hacksaw blade that's clamped to a post. The other end is free. And we want to draw a graph showing the 2 lowest harmonics that can occur on the hacksaw blade. And we want to know what the wavelength of each of those harmonics is in comparison to the length of the blade. So there's the post, and there's the hacksaw blade. And you know that if it's clamped to that post, that point where it's clamped has to be a node. It's not going anywhere. It's not vibrating, okay? But what we're going to find over and over again on Thursday when we talk about organ pipes is that if I have a free end, that's always an antinode, okay? So in this case, the fundamental wavelength, the lowest wavelength that will resonate with this goes straight from the node to the antinode like that, okay? How many footballs do I have there? Half a football, okay? You remember when the ends were the same, when I went from a node to a node, I always started with a full football. But if I start with one side being a node and one side being an antinode, I start with only a half football. Well, how much of a wavelength do I have there? Yeah, if it takes two footballs to make a wavelength, I've only got a quarter wavelength. And so the length of the hacksaw blade is just a quarter of the wavelength. And that means the wavelength for this first harmonic is 4 times the length of the hacksaw blade. Not 2 times, but 4 times. Okay? We still call that the fundamental or the first harmonic because it's the lowest frequency that will resonate with this system. It's the longest wavelength and hence the lowest frequency. Now here's where it gets weird, okay? When I go to the next allowed resonance, I've got to add a whole football every time I go to the next resonance, okay? I still have an antinode at the end, but now I've got to have both an antinode and a node added in there. And so I'm going from half a football to 3 half footballs. Everyone see that? I've got a football and a half, 3 half footballs. Let me back up. If I start a system that goes from node to node, I start with 1 football. Adding another football doubles the number of footballs. But in this system where I go from node to antinode, I start with half a football. So adding another football triples the number of footballs. If I add yet another football, I'm going to go to 5 half footballs. I'm going to increase the number of footballs by 5. Okay. Now, if I went from half a football to 3 half footballs, I'm tripling the number of footballs that fit on that hacksaw blade. They have to get 1/3 as big. And so that means they are going to be 1/3 the original wavelength. And we have to call that the third harmonic if we want to still use our formulas, okay? So that's the wrinkle. When the ends are the same, either they're both nodes, or we're going to see on Thursday they can both be antinodes. We start with 1 football, and then we've got 2, and then 3, and then 4, and then 5, and then 6 forever, okay? We get all the harmonics, F1, F2, F3, F4, F5. But if they're different, if one's a node and one's an antinode, I don't get any of the even harmonics. I go from F1 to F3 to F5 to F7 to F9 to F11. Talk to your neighbor. Talk to your neighbor.
I got one down, but you automatically all the time. Oh. Yeah.
It was just it's like, oh, we're not in shaking.
I get it, and here's.
Now,
I don't like.
it'd be very, very, very difficult, probably impossible,
Like you're starting.
to excite the 23rd harmonic on this system, on this hacksaw blade. But if I could do it, how many footballs would there be in the 23rd harmonic? Talk to your neighbor about that.
Third harmonic, you know. Yeah, I mean, the point right there.
Who's harmonic?
One and a half.
Just one. One and a half of both. Every house, half of it.
Okay, I know for a fact, because I'm an old man, that some of you are making this way harder than it really is. If I start on this hacksaw blade with only half a football in the first harmonic, the 23rd harmonic is going to have 23 times that many footballs, or 23 half footballs. And 23 half footballs is the same as 11 and a half football, right? That makes sense? Okay. So this is the summary slide that you're going to see over and over again this week. When the ends are the same, and that means they're either both nodes or they're both antinodes, I get all the harmonics, F1, F2, F3, F4, to infinity and beyond. If the ends are different, one's a node and one's an antinode, I only get the odd resonances, the odd harmonics. Yes, sir.
What's the name of the system where you have one node and one antinode? Is it just
I can't hear that. What did you?
Name of the system that has one antinode and a node?
I'm sorry.
And what is the name of the system that has an antinode and a node?
Just ends are different. Yeah. When we talk about organ pipes, we'll find that a closed organ pipe is an example of that. A flute is an example of that. But we'll talk about those longitudinal standing waves on Thursday. Okay. Now, every system has these resonant frequencies and these resonant wavelengths, and the more complicated the system, the more complicated these resonances. Now here I just have a square piece of metal hooked to a vibrator that goes up and down at a frequency that I can control. And I'm gonna let you look at, I put salt on the piece of metal. And if I drive it with a frequency, what you see is that it starts to make a pattern. And that's because the places where I've got an antinode is pushing salt out of the way. And the places where I have a node where it's not moving, that's where the salt is congregating. So let me see what shapes I can make. Now I know that 1347 has a resonance. Oh, we're getting close to it. Here's another one. Okay. Yeah, we could look for these all day, but that's, we don't need to do that. In case that didn't work, I found an example online. Okay, that's fun. Okay. Now, I have for your enjoyment two sample exam questions that we can go through. I placed 2 sample exams and their solutions at the MAC site this morning. So when you feel comfortable doing that, do I have helpers over here that can? Thank you so much. Mr. Rogers says, look for the helpers. Okay, there's a helper. Over on this side here. Another helper over here. Anyone? Oh, thank you. Okay, so if you pass the bread down this aisle. Now, in this problem, we have an oscillating string that I'm going to get it up closer here. Okay. So our string is 3 meters long. It has a mass of 40 grams, which is 0.04 kilograms. And it's attached to a ring that turns out to be massless and moves without friction. Now, that just screams out from that first tutorial, the first tutorial homework, free end. And we said that a free end is always an antinode. On the other hand, this place where the string goes over the pulley, this heavy weight of 30 kilograms is holding it down so that it really can't move very far from that pulley. And so what we're going to see is a node there and an antinode there. Now, just to give you some points with your clicker, now you can click. What kind of system is this? Ends the same or ends different? Or I'm skiing. I wish I was skiing. We should get 100% on this, people. I just told you what the answer was. This is a celebrity Jeopardy problem. Can you point to your own head? Okay. Okay, last call. Is that everyone? I'll take it to be everyone. Whoa, we almost got to go to Disney World, but no. There were some people that went the other way. Okay. So those are ends different. We have got a node at one end. This is where the vibration is happening here. Okay, in that 2 meter length. And it's a node at this end where it's essentially clamped down, and it's an antinode where it's free to slide up and down that rod. Now, I'm going to skip ahead to C and D here. They ask us to draw the lowest frequency standing wave in this picture and the next lowest in this picture. Well, if this is a node and this is an antinode, the fundamental frequency is the wavelength that is the longest wave that'll fit those boundary conditions. The longest wave is the lowest frequency, okay? And so that would go right from the node to the antinode. And that would be the fundamental, or F1. And there's a hack football there, just like with the hacksaw blade. Just like we saw when the hacksaw blade went from a node to an antinode. Now, the next lowest frequency, if this is a node and this is an antinode, I have to add another node and another antinode. And so this is going to be So this would be an antinode, this would be a node, this would be an antinode. And you'll see that I've tripled the number of footballs that fit on that 2-meter length of string compared to the first harmonic. And so this is going to be F3. If I've tripled the number of footballs that fit in the same space, the footballs had to get 1/3 as big. That means the wavelength had to get 1/3 as big. That means the frequency by the wave equation had to get 3 times as big. Okay? Now, I hope this is okay, but I noticed that online, well, that's not good. Oh, okay. So I need my lamp. Okay, now I can turn off the light. Okay. I just want people online to be able to see what we did there. Okay. Any questions? I can't see your hand, so I guess there's none. So let's go back up here to the top. What is the tension in the string? Well, I know if I draw a free body diagram for that block, a 30 kilogram block is going to have a weight force, earth on the block, of 30 kilograms times 10 newtons for each kilogram. It's 9.8 on our planet, but we're going to go to that other planet where it's 10. And that gives me 300 newtons. And that means that the tension force by the string on the block, since this isn't really going anywhere, has to be 300 newtons. Okay. Now, part B asks us to find the wave speed in the string. Well, because this is a transverse wave, we're going to use the formula for transverse wave speed, which is the square root of the tension over the mass density. Okay. Now, the tension we said was 300 newtons, but we need the mass density. Well, the mass density is just the mass of the string divided by the length of the string. Now, we're told that the mass of the string is 0.04 kilograms. But what's the length of the string? And I'm not being facetious. When this was on an exam, this split the class in half. Half of them wanted to make that 2 meters and half of them wanted to make it 3 meters. Tell your neighbor how you'd come down on that argument. Was it 2 meters or 3 meters?
3 meters. Providing the death variant.
And even worse.
Okay. Now I hope you can see why there's confusion. The string is 3 meters long, but only 2 meters of that is playing with our game, is making the oscillation. But if we want the mass density, we want the length of string that actually has a mass of 0.04 kilograms. And that was given as the mass of the whole string, all 3 meters of the string. And so I have to divide by 3 meters. And that's going to give me 0.0133 to infinity beyond kilograms per meter. Okay. Now, if I plug that in up here, 0.0133, kilograms per meter, I get a speed of 150 meters per second. Are we okay with that? Since I can't see your hand, you're gonna have to shout.
Yeah.
Okay. Let's go down to E now. Was there a question? No? Okay, E asks us for the frequency of the standing wave that we drew in part D. Now, again, I can't draw a frequency. I can hear it, but I can't draw it. And so I'm going to have to use this grand high wave equation to get that frequency. Now, in your toolbox, there are two equations that are more important than all the others. And that's because they always work for every kind of wave, whether it's a traveling wave or a standing wave, transverse wave or longitudinal wave, doesn't matter. And those two equations are the wave equation, V is equal to F times lambda, and this football equation that we used when we were looking at the different resonances. The number of footballs times lambda over 2 is equal to the length of the system. Okay, since each football is half a wavelength, I just add up how many footballs I have, and each one is half a wavelength. Okay, well, let me show you how I use those two equations to solve this problem. The wave equation, V is equal to frequency times wavelength, works for every harmonic. It works for the first harmonic. It works for the third harmonic. It works for the fifth harmonic. Whoops. But you always have to use, if you're looking for the fifth harmonic, you've got to use the fifth wavelength. Okay, never mix and match. That. Okay. Now, since I'm looking for the third harmonic, I'm going to use this equation here. And what that tells me is that the speed, 150 meters per second, is equal to the third harmonic times the third wavelength. So if I knew what the third wavelength was, I'd be done. Well, let's use that football equation. Number of footballs times lambda over 2 is equal to the length of the string that's resonating. So here I've got 3 half footballs, lambda 3 over 2, whoops, that's times, my mistake, over 2 is equal to the length of the string that's resonating, which is 2 meters. And that gives me that the lambda for the third harmonic is 8/3 meters. Does everyone see how I got that? I just multiplied both sides by 4 and divided by 3, and this became 8/3. Okay? Well, now I can plug that up into here. 150 meters per second is equal to F3 times 8/3 meters. That's just math. That's just your calculator. And that's going to give you F3 is equal to 56.25 hertz. Check on your neighbor in the dark. Do a buddy check.
I have a question over.
Oh, question over here.
Where is the after 2?
And if they want the third.
W? Here, okay.
Oh,
It's 100.
this right here,
It is over. There you go.
that's an M, meters.
Oh, credit.
Is there a question there? Oh, okay.
Yeah.
Okay, let's turn this page over. In this problem, we have a 50-kilogram block and it's suspended from the ceiling by a length of wire. We know the mass of the wire is 0.1 kilograms, but we don't know the length of it. We find that if we jiggle the block at just the right frequency, we can set up the fifth harmonic, and we're first of all asked to draw that fifth harmonic. Well, where this wire is attached to the ceiling has to be a node, and where it's attached to the heavy block has to be a node. So this is one of those where the endpoints are the same. And so I start with one whole football. And each time I go to the next allowed resonance, I add one more football. So I'm going to go from one football to two footballs to three footballs to four footballs to five footballs. So the fifth harmonic would have 5 footballs, 1, 2, 3, 4, 5. And all of those are the same size, I promise. If you just look at, squint your eyes, and they'll all be the same size. You know I can't draw. Now, I don't know what the length of this wire is, but I would sure like to know what it is because they're asking me to find the mass density of the wire. And the mass density of the wire is equal to the mass of the wire divided by the length of the wire. Well, the mass of the wire is 0.1 kilogram. That's given in the problem. But what's the length of that wire? Well, that football equation, we can dance both ways. If we know the length of the system, we can use it to find the length of the football. Or if we know the length of the football, we can find the length of the system. So let's use that football equation. Okay, in this case, I have 5 footballs, and I know that this is the 5th wavelength, and we're told that the 5th harmonic has a wavelength of 0.8 meters. So I'm going to plug in 0.8 meters, and I got to divide by 2, and that's going to give me the length of the wire. Well, 0.8 divided by 2 is 0.4. You multiply that by 5 and you get the length of the wire is equal to 2 meters. So now if I plug that in up here, 2 meters, what I get is a linear mass density of 0.05 kilograms per meter. Okay, check on your neighbor. Well, now, the last thing we're asked for before we leave is the frequency of the 5th harmonic. And we can use the wave equation. I know the wavelength for the 5th harmonic is 0.8 meters. I'm looking for this, the frequency of the 5th harmonic. I just need to know what the speed of waves is on this system. Because it's a transverse wave on a string or wire or spring, I use this formula where I take the square root of the tension divided by the mass density. I think we can all see that the tension, if I'm hanging a 50-kilogram block, is going to be 500 newtons. That's the weight. And if I divide that by 0.05 kilograms per meter, I get a wave speed of 100 meters per second. Okay. Well, now let's go back up here and plug in V is equal to F5 lambda 5. If V is 100 and lambda is 0.8, then I can solve for F5, just 100 meters per second divided by 0.8 meters, or 125 hertz. Okay, I'm going to turn on the lights so that we can ask questions. Questions? Good, sir. Second. Thank you for asking that. This gentleman just asked a very important question. The wire has mass. So when we're looking for the tension in that wire, it's only 500 newtons at the place where it's touching the block. If I look up higher, that's going to be 501 newtons. And what I'm telling you here is that if when you walk out that door, someone gives you $500 and someone else gives you $501, you're the same happy, okay? We always make the block very big compared to the wire. Okay, have a great evening. Somewhere else. Welcome. See ya.